Okay, so imagine this.
You're handed this box, right?
Yeah.
And it's totally sealed up. You have no idea what's inside.
Yeah.
Could be anything. Clockwork gears.
Wires buzzing with like electricity,
Right.
maybe even a bit of AI code in there. Who knows? But
Right.
you've only got a limited number of tests to figure out what makes this thing tick.
Okay.
So how do you get the absolute most information
Out of each of those tests.
That's a question that pops up everywhere, right? I mean, not just with physical things like that,
Oh, yeah.
but any system where, you're working with limited resources and you've got a lot of unknowns.
It's like the ultimate puzzle.
Yeah.
And that actually leads us perfectly into today's deep dive.
We're cracking open this really elegant idea from set theory. It's called shattering.
Okay.
And it has some surprising connections to, get this, machine learning.
Yeah. And we're going to see just how important it is, understanding the limits of this whole shattering thing.
If you want to build smarter algorithms, if you want to send data across the galaxy without, losing a single bit.
Whoa, okay, hold on.
So shattering sets, it sounds kind of intense.
But it's actually pretty intuitive once you wrap your head around it. Imagine shining a beam of light through a prism.
Okay.
The light, that's like your set of information.
Mm-hmm.
And the way the prism splits that light into all its different colors.
Right.
That's what shattering is all about. You're basically revealing every single possible subcomponent, every subset.
It's hiding within that larger set.
And to actually represent this splitting mathematically, we use something called a binary matrix.
Okay.
So think about a grid.
Where every single cell, you can have a 0 or a 1.
Okay.
Each row, that's like a subset.
And each column represents, an element from your original set. So a shattered set.
You're going to see every single possible combination of those zeros and ones.
So let me see if I'm getting this. If our original set had, say, 3 elements.
Our matrix, it would need to show all 8 possible combinations of zeros and ones in its rows.
Exactly. And that's how we know that family of subsets fully shatters that original set. You've revealed all of its hidden parts.
Okay. This is starting to click a little bit.
But I have to ask, why should I care about shattering sets? This seems pretty abstract. Like, what's the practical application here?
So that's where things get really, really interesting.
Right.
This isn't just some theoretical math puzzle, okay?
Right.
This has real-world stuff going on, especially in machine learning. So let's say you've got an AI, and it's learning to tell the difference between, we'll keep it simple, pictures of cats and pictures of dogs.
Sure.
Understanding shattering actually helps us design these algorithms that can learn these categories crazy fast, even with like millions of different cat and dog photos out there.
So instead of showing the AI like every single cat photo and every single dog photo ever taken,
right,
it can use these shattering principles to be like, okay, these are the key features that tell them apart.
Exactly. And it goes way beyond just image recognition too. Think about error correcting codes. The stuff that makes sure your Netflix stream doesn't buffer, or that NASA's getting a clear signal from, probes in deep space.
Shattering helps us build those codes so that even if parts of the data get lost in transit, we can still reconstruct that original message perfectly.
So it's all about figuring out, like, how much information can we pack into a system?
Like cramming as many songs as possible onto a hard drive.
Yeah.
But for any kind of information.
That's the heart of information theory.
And it's really deeply connected to this whole idea of shattering.
How do we maximize the amount of information, but also the reliability of transmitting that information?
This is blowing my mind a little bit.
Okay, so we're talking about the limits of shattering.
Yeah.
But what's the actual puzzle that these researchers, the authors behind this paper, maximum shattering?
What are they trying to solve?
So their big question is, if we've got a certain budget of sets that we can work with, what is the absolute maximum number of subsets that we can shatter?
Like, imagine it like a game, right? We're trying to rack up the highest possible score given these certain constraints.
So they're looking for, the ultimate winning strategy. The best case scenario, no compromises.
Precisely. And that's really valuable because it gives us, this theoretical benchmark, a kind of speed limit for information processing itself.
Okay, I'm hooked. Now let's get into the nitty-gritty of how they actually figured this out.
Oh, and they really will go deep on the math to get there. I'll give you that.
Yeah.
But the cool thing is...
Even with all those crazy equations, the core ideas are actually pretty intuitive once you get past all the symbols.
Okay, so their main result, this is theorem 1.1, in the paper, it's kind of like the recipe.
For achieving this maximum shattering, right?
Like that.
What are the main ingredients, so to speak, that we're working with here?
So they're thinking about things like the size of that original set that you're working with.
Okay.
How many subsets you have in your budget, so to speak.
And how big those subsets are that you're trying to shatter.
Okay.
It's all about, like any good recipe.
It's all about finding that perfect balance.
So instead of ending up with like a delicious cake or something,
Yeah.
we're aiming for like the most shattered subsets possible.
Exactly. And so theorem 1.1, it basically gives us this formula to actually calculate that perfect balance.
Yeah.
Say, all right, given what you're working with, this is exactly how much shattering you can squeeze out of it.
Now, I will be honest, the formula itself,
it's got some pretty intense symbols in there, you know?
Yeah.
The kind that might give someone, like, flashbacks to high school math class.
Yeah.
But not in a good way.
Right.
More like a, oh no, I'm having a nightmare kind of way.
But don't let the notation freak you out too much.
Okay.
Because what's really cool here is this unexpected connection it has to something called linearly independent vectors.
Okay, hold on. Vectors, like on a map.
Kinda, yeah. You can think of it visually.
Like, imagine we've got a cookbook open.
And it's open to, I don't know, the recipe for, like, the best bowl of ramen you've ever had in your life.
All right, I'm with you.
Each ingredient in that recipe, that's like a vector.
Okay.
And linearly independent basically means that each ingredient...
it brings something totally unique to that flavor, right?
Yeah.
You can't just make that ingredient.
by mixing the other ones together in some way. Each one is doing its own thing.
Okay, I think I'm following so far. So we've got our unique ramen ingredients, each one bringing something special to the table.
But how does that relate to shattering sets?
Yeah.
I'll admit, it's not immediately obvious.
And that's the beauty of it, right? The formula in Theorem 1.1, it actually uses the probability of these independent ingredients, these random vectors, as a key part of figuring out how much shattering can we actually achieve.
Mm-hmm.
So it's like these totally different ideas are kind of woven together in this really, really neat way.
It's like you're discovering these hidden patterns in, like, the universe of mathematics. But this Theorem 1.1, it seems pretty, general, right? It's a big rule. What about when we want to get down to brass tacks, to very specific scenarios?
Yeah, absolutely.
That's where Theorem 1.2 comes in.
Okay.
They're zooming in on what happens as the sets that we're dealing with.
They start to get truly massive, like unbelievably huge.
So if we just keep adding elements to our set, like forever...
Does the number of subsets we can shatter, does that just keep growing forever too?
This is where things get really mind-blowing, okay? It doesn't. What they found is that as those sets grow infinitely large, the maximum shattering we can hit actually kind of settles down around a specific value, which is roughly 0.289.
Oh, hold on.
So there's a ceiling on it.
There's a feeling.
No matter how big that system gets, there's like a fundamental limit on how else we can actually shatter it.
Yeah, it's like we've discovered, a fundamental constant
in the universe, but for information itself.
That's kind of unsettling, honestly, but also really cool. Like a universal speed limit, but for information.
And what's even more exciting, I think, is that this paper doesn't just answer questions.
It opens up a whole bunch of new ones.
Oh.
The researchers themselves point out that there's still so much that we don't know about maximum shattering in, more complex cases beyond the specific ones that they were looking at for this paper.
So even in this, like, incredibly,
what seems like a niche corner of math.
Yeah.
There's still mysteries waiting to be uncovered.
Absolutely, tons of them.
I love that.
That's what makes it so fun.
Okay, my brain's still buzzing a little bit from that 0.289 thing.
That's going to stick with me for a while.
It's a wild thought, right?
It really is. But before we get, like, lost in space with all these theoretical,
equations and stuff.
Yeah.
Remember that mysterious box we were talking about at the start?
Oh, okay.
With all the gears and code and...
Yeah.
How does this shattering idea, how does that actually help us unlock the secrets of that box?
So think of it this way.
Okay.
Every test you run on that box.
It's like you're picking out a specific subset of its components.
And seeing how they interact, right?
Okay.
The more you can shatter the system with those tests.
Meaning the more unique combinations you can explore,
right,
the more of its inner workings you're going to reveal.
So each test is like shining a beam of light in there, and we're trying to hit every single corner, figure out how it's all connected.
Exactly. And the cool thing is...
even if you can't test every single combination.
Right, because with a really complex system, like, good luck with that.
Exactly. But even then, understanding shattering, it helps you design those tests strategically, right? It's about getting the absolute most insight. with the limited resources that you have.
It's like you're getting the most bang for your buck, but with information.
There you go.
This is incredible.
It's amazing to me how this kind of abstract math concept,
yeah,
it can be applied so broadly.
It really can.
It's like this idea of maximum shattering. It's almost like a blueprint
for understanding any complex system, whether we're talking about a machine or even a relationship or a whole society.
It's a framework for thinking,
Yeah.
It's not just about the math itself.
This deep dive has been honestly mind-blowing.
We went from shining light through prisms to uncovering the fundamental limits of information itself.
And how to build a smarter AI along the way.
Oh yeah, can't forget about that. And it all comes back to this idea of shattering.
It's all connected. It's been a pleasure geeking out about this with you.
Likewise. And for everyone listening out there, here's a little something to think about.
Okay.
Where else in your life, right, do you encounter systems with these, hidden depths?
Yeah.
Where could you apply this principle of shattering?
Of really maximizing that information gain with whatever resources, whether it's time or energy or money.
It could be anything, yeah.
Maybe it's a project at work.
Maybe it's a creative challenge you're going through.
Or even something as personal as understanding your own habits or your motivations.
Yeah.
The next time you're facing a complex problem, just ask yourself,
what are the most insightful tests I can run here to really reveal how this thing works?
I love that. Keep that question in mind.
And who knows what you might discover.
That's all the time we have for today's deep dive into the world of maximum shattering.
Thanks for joining us, and as always, keep exploring.